Hello, and welcome back to Watch This Space, our flagship series here on Haberdashers Adams Astronomy. Now, in our first series, we looked at the moon, with me making and painting this lovely model to illustrate the different features and aspects of our nearest neighbour. Now, for our second series, we are looking at stars, and it didn't quite seem appropriate to just make a polystyrene model of something that's a bit more dynamic, a bit more interesting than that. So over the first 3 videos of this series, we're going to be looking at the life cycle of a star, and to help illustrate our points, we will be using paintings like this one here, where we will take you all the way from this, a nebula, through today to main sequence stars to look at the birth of a star.
3, 2, 1.
Stars.
All stars begin their lives as a nebula, a giant cloud of dust and gas on the scale of an entire star system. Which gases, you may ask? Now, this varies depending on when the nebula formed. If the nebula was created in the early universe, there won't have been previous generations of stars before it, meaning that it will be around 3/4 hydrogen, 25% helium. This is because the early universe was briefly hot enough for hydrogen to fuse into helium, but as the universe expanded and cooled, it didn't fuse all of the hydrogen, nor did it fuse the helium into any heavier elements. Later nebulae will have much the same composition, but will also include elements that are remnants of previous generations of stars that existed in the same region of the universe. When you look at different nebulae, you probably notice that they are a variety of shapes and colours. This is in part due to the fact they're formed of the material ejected at the end of other stars' life cycles, which then means their mass is not uniformly distributed, with more dense regions capable of pulling other parts in towards them. Different coloration also occurs due to the mix of other elements that are present in the nebula and the range of temperatures in the cloud at different points. The vast majority of energy within a nebula is stored as gravitational potential energy due to the huge scale that their mass is spread over. The regions where the mass is most closely packed together can cause a collapse of the entire nebula over the course of hundreds of thousands to several millions of years. As more mass gets pulled into the regions of higher density, the gravitational potential energy transfers into kinetic energy, and the region becomes even more dense. This then further strengthens the force pulling on other mass in the nebula, which will accelerate the collapse. To form a star, the high-density region must get up to around 1/12 the mass of the Sun. This means that not only is it possible for more than one star to form from a singular nebula, but the majority of star systems created are binary systems. A small proportion even form into trinary or triple star systems, though understandably the orbits on these can be a little bit complicated. The remaining matter that isn't pulled into what will become the star or stars in the system will form the planets, moons, asteroids, comets, and whatever else is going to make up that star system. This will be a minute fraction of the overall mass though. In our solar system, the Sun has around 99.8% of the total mass. Before the nebula becomes a main sequence star though, it goes through an intermediary stage known as a protostar. As a nebula collapses, the central mass will pull in more and more matter. This allows this central mass to become more spherical in shape and to gradually heat up. So this is because the matter that's falling in towards the central mass tends to spiral inwards as an accretion disk, a little bit like coins on the charity coin spinners you might find at a garden centre or supermarket. The gases will rub against each other as they collapse inwards, transferring their gravitational and kinetic energy into thermal energy. When the star has reached this spherical shape, it is classified as a protostar. There is no nuclear fusion taking place in the core yet, as its temperature is not high enough for the positively charged hydrogen nuclei at the centre of the protostar to overcome their repulsive forces from one another. At this stage, the forces on the star haven't quite balanced either, and the inwards gravitational forces are larger than the outwards pressure forces. So they continue to collapse with a rising core temp until it gets hot enough for nuclear fusion to start, at which point they enter the main sequence phase. When the core temperature of a star reaches a high enough temperature and pressure, the hydrogen nuclei reach a high enough speed to overcome the resistive forces trying to repel them. When they first fuse together, this releases energy and provides an outwards nuclear pressure force that slows and then stops the collapse of the star. It has now reached the main sequence stage, where it will likely spend the vast majority of its lifetime. During this period, the forces in and outwards on the star balance, giving a long period of stability and consistent core temperature, which allows the fusion of hydrogen into helium to take place. This isn't a single-step process though, with the vast majority of fusion taking place via something called the proton-proton chain, which works like this. So initially we have two regular hydrogen nuclei, so essentially protons, smashing into each other. They form an isotope of hydrogen called deuterium. So one of the protons is forced under the extreme conditions into becoming a neutron. The second stage, we can see another regular hydrogen, so a proton, coming in and colliding with that deuterium, and this gives us helium-3. This isn't the regular version of helium though, and there's more energy to be released if we can form helium-4, which has a much higher binding energy. So what we want to do then is we take two helium-3s, I say we, the sun does, smash them together at really high speeds, and you get yourself helium-4 and a couple more protons so that you can carry on the chain. Each individual fusion chain only releases a small amount of energy, meaning that to maintain that outwards nuclear pressure force, a huge amount of fusion needs to occur each second. In the sun, for example, over 600 million metric tons of hydrogen are fused every single second to provide its power output of almost 4 × 10⁻26 watts. The amount of fusion taking place in a main sequence star depends on its size, with larger stars needing a higher rates of reactions to maintain their size versus smaller ones. As a result, the largest main sequence stars will last much shorter on this phase of their life cycle, as they burn through their hydrogen at a much faster rate. You can think of this to being similar of how a typical muscle car with a huge engine would achieve a much lower miles per gallon than a hatchback, meaning that they often have to top their fuel up much more frequently despite having a larger fuel tank. Now obviously for stars, they can't just top up their fuel, so once it runs out, it runs out. A main sequence star only fuses hydrogen into helium. To fuse heavier elements would require a much hotter core. It will continue this fusion in the core until it's combined enough hydrogen to reduce the purity of the core to a level that makes it impossible to continue this fusion at a consistent pace. This ends the main sequence and also ends the point where all stars take the same path on their evolutionary journeys. So that is how stars are born. But what happens next? That's what we'll be looking at in next week's episode, where we will specifically look at the lower mass stars. So what would happen for something that's lighter than the Sun, or even sun-massed, once they finish that main sequence phase. If you're bored between now and next week, though, that is perfectly natural. But something you can do to fill that boredom is watch one of the other videos from our channel. Please do let us know if you've got any recommendations for what you'd like to know about stars and constellations in the comments. We might be able to add it to the to-do list for this series of videos. Give us a like and subscribe if you haven't already. And until next time, please continue to watch this space. Thank you.